right, start finishing up, please. All right, everybody, let's come together on this. Everybody settle down, please. Okay, so we got a couple different types of problems here. On the first one, it says an 190,000 watt engine can accelerate from rest to a top speed in 9 seconds. All right, how much work did the engine do? Right now, remember, what's the formula for power? Okay, the power, don't like that much. Power equals work divided by time. Okay, so therefore, work equals power multiplied by time. So, what we can do then is do 190,000 watts multiplied by 9 seconds. Okay? And according to our super calculator here, you get 1,710,000 joules. All right? Okay, any questions on that? Everybody got that? No big deal. Okay, so next one, another engine reaches top speed in 7.5 seconds. It's able to perform this much work in that time. So, again, power is work divided by time. So, we got 250,000 joules divided by a time of 7.5 seconds. Okay. By 7.5 is 33,333-ish. Lots of threes. Watts. Okay. Now, here's the other way that you can do it, right? Is to solve for time. Right? So power is work divided by time. And power times time equals work. Then work divided by power, right? Are you with me? Okay, so time is work divided by power. So, 350 joules divided by 125 watts. I can't remember my calculator. .8 seconds. All right? Questions on that? All right, so since work is force divided by distance, or work is force times distance, then Miles, did you get how much work this girl does? Yeah. Joules, right? Okay? So, how much energy is used? Yeah. Okay, so work is force times distance. So you have 300 newtons times a distance of 750 meters, and that's going to get 225,000 joules. Okay? All right. Yep, just multiply the two. Okay? So, kind of an interesting question. The second, and B, how much energy is used? Well, the first thing I would say is, okay, how much energy is used by what? By whom, right? Because if you're the sled or the little brother on the sled, no, you're not using any energy, right? You're getting the free ride. But specifically speaking, that the little girl, how much energy is the little girl using? And I'll give you a hand. If you're calculating anything, then you're not right, then you're incorrect, probably. Because you already calculated. How do you do work? Oh, come on. After work, you're tired, right? Why? Because you used energy. So how much energy is used by a little girl? What? Well, that's how much force. But how much energy is this, right? Same thing. Because if there was that work done, then there had to be somebody using the energy or something using the energy to do the work. So the work is going to be equal to the energy is going to be equal to the work. It has to be, right? If you do work on anything, the energy has to be put into the system. Okay? Next, how much power does she use if it takes her 25 seconds? What are you going to do? Power is work divided by time, right? Okay. 25 and you get what? 9,000? Yeah. And that would be 9,000 watts of energy. Okay? So again, the faster that she does it, the higher the power is going to be. It's not going to be any more work, right? But the point is, how fast is the work done in terms of power? Okay. So then if we change it to 10, we're just going to divide by 10 instead of 25, right? Okay, then now how much work? Or not how much power? Oh, come on, who was calculating back there? Oh man, come on. Come on, man. Divided by 10 instead of 25. Yeah. So 22,500. Okay? So, remember that those inverse and those direct relationships, power is an inverse relationship with time. The faster something's done, the more power is involved. All right? Okay. So, going on to this one. All right, Kylie. This one. How much work is done does he do on a wall? Okay. What? Okay. Anybody get this one? Or if you didn't get this one, you know what it is right now because you should. There's a part of this sentence that's really, really important. What does that mean? Zero work, right? Because work is force times distance. And if that distance is zero, there's no work, right? Okay. Okay, 0 joules. How much energy is used? Now this is one that's complicated. We have to stop thinking about it in terms of our life and the poor person pushing on the wall and getting tired. Yeah. Yeah, how much energy does he put into the system? All right, because if we think about this in our normal terms, then we probably don't know enough. But since no work is done, how much energy is put into the system? 0. All right? And since no work is done, how much power is exerted? 0 watts. Okay? Don't think about it in terms of the exertion. Think about it in terms of what actually happens to the system. Those objects have to move in order for work to be done. All right? Okay, so now I know my plan for today is we're going to get through the rest of these machines here. And talking and reviewing mechanical advantage and all this good stuff. Now, now what I think you probably really want to know is about the exam next week, right? So I guess if memory serves, we'll have it on Tuesday, right? First thing on Tuesday? Okay. So, what I'm going to do in this unit is, in my opinion, a super important unit for the class. And because I didn't really get a chance to test you all on it, like as a real test in person and all this good stuff, what I'm going to do is I'm going to make the semester exam into like a really big test on energy. So the only thing that'll be on is energy. Nothing else. Right. So we're going to make a study guide with respect to this topic, but not for the stuff that's not going to be on. Energy. Right. Now, the other part of that is, of course, there's, Newton's laws come into play here, and also speed and that good stuff anyway. So I don't have a problem with doing this, and because that's the good question, and I don't know. I haven't decided yet. Here's the debate, DJ. The debate that goes on in my mind. Like, you all wanted all multiple choice, and I wanted all multiple choice, because multiple choice is easier for me, too. However, if we look at student performance in this group and in all groups I've ever taught in my history of teaching. Students do better on written than they do on multiple choice.
Trust me, I do not do better.
Okay? Now, there might be a few exceptions to that, but by and large, students do better on written than multiple choice. And it's usually by about 15 percentage points. So, that's where I'm kind of debate, but we'll see. Well, I just have to decide what I want to do, and then we'll kind of go with that. So on Wednesday, I'll tell you exactly what I decide to do. But for right now, I think we're just going to finish this up and make sure everyone is on the same page with mechanical energy. Yeah. Okay. This stuff. Yeah. Okay. Now, sorry, I feel like that mask just kind of muffles me a lot more. So, I will change it. All right, so, but I think overall that's good news because that's less stuff to worry about in terms of topics. But, and then what I'll probably do, I don't know. What I was thinking about doing was if people do well, I'll use the percentage for the semester exam and as a final test on this quarter. Like kind of a double thing.
I don't know if I like that. Wait, if we do well?
Yeah, don't forget that prepositional phrase. If you do well.
If we do bad.
No, if we don't, we should be able to see the grade and then.
Well, what would be funny is like you have to come in and you have to choose before you take it.
Just curve it.
Like gambling.
I want to curve.
How about we make the choose if we take it?
I like that. Yeah, how about we see
Then we just do the semester exam.
Come on.
So I don't know. I don't know what I'm gonna do. But
Mr. Tillman, can our test be on personal questions, like we have to answer about ourselves?
Yeah. Like how old am I?
there might be some of that, but yes.
If we're up,
Yes.
are there possibilities of being exempt?
Not for this one.
Oh.
Second semester, yes. Well, typically it's like you have to have an A average for both quarters.
Yeah, never mind. I don't work on that.
Yeah. Third. Yes. Probably not, but we'll see how it goes.
I said just go curve. Just help us. We're under a lot of pressure.
Well, I think that we'll come up with a good response to this. But what I want to do, though, everyone, listen up. What I want to do is, again, to get through this, and then you guys can ask whatever questions you have. And next class, then we'll kind of go through the test, and I'll give you some of my ideas for the answers for the quiz that you guys did take remote. And then we'll kind of go from there. Emily, did you have a question? It's not? It shouldn't be blocked. Hi.
Is there any possibility you could give us all the questions and all the answers to the exam before the exam takes?
Yeah, what would be the fun of that?
Because then my grade goes from being pretty good.
Yeah, can we have a group exam? Or, like we said, we can all take the exam.
Well, see, the problem with group exams is that if you get a group exam, then like I have to make it harder. Go ahead, Emily.
If it's a group exam, you can actually make it easier.
I could, but I probably wouldn't.
So, Mr. Tillman, I gotta ask,
Yes.
why do you want our exam to be so hard?
I don't want your exam to be hard. But it's like I have my own teaching philosophies that I kind of have to adhere to.
So if you're not worried about it,
I feel bound to.
it's easy, so my grade.
Okay.
See, but
conversation with my dad.
I know, well. I'm sure I'd love to sit down and talk with your dad. What? Why? With your dad?
He says dad is pretty tough.
He's Donald Jr., so I'm assuming his name's Donald. All right, well, that's all right. All right, let's go ahead and look at these. So, when we were talking, I guess last remotely, we were going through this idea of mechanical advantage. I think there's someone out there. Emily, Emily. So when you talk about mechanical advantage, basically what it is saying that this machine is either allowing you to increase the force that's involved, right? Like you put in 2 newtons and you get 20 out. Or sometimes it's direction, right? With a pulley, where you can, it's easy to push objects forward maybe, but to move them up 20 meters or something is hard, so a pulley would be helpful in that. Okay, Nate?
You can just head out now, go online.
Okay? So, when mechanical advantage comes about, basically it's just allowing us to do other things with the work that's put into it, right? Now, the simple machines were kind of the ones that were developed in the beginning, certainly before the Industrial Revolution, where machines, gentlemen, focus, where machines connected to engines, right, to the internal combustion engine, kind of took over, like big tractors and whatnot. But they were all based on these simple machines and these simple ideas, right? So we talked about the screw and how the screw is kind of like an inclined plane, right? So now, how does an inclined plane help us? Okay, it does give mechanical advantage. But how? What does it do? Right? All right, remember work is good. Now look, remember work is force times distance. And this work, like if I'm picking this box or this thing up and putting it to a higher place, like up here, the work involved in it would be the same, right? If I pick this thing up and put it on here, because the potential energy is the same from the floor to the table, right? And it doesn't matter whether I do it this way or if it was like over here and we had a ramp and pushed it all the way up, it's still going to be the same amount of work. So, when I increase the distance, if it's the same amount of work, what is going to happen to the force? You increase the distance, the force goes down, right? Because this value is going to be the same. All right? So, we would say that when distance goes up, force goes down. And I mentioned, I think remotely, the pyramids and the possibility that this was how the pyramids were made, because they just made like a big series of ramps. Instead of lifting it from the bottom to the top, they just kind of did it on a much bigger distance, therefore making the force smaller, because the human beings couldn't move those blocks. They couldn't pick those blocks up because they're several hundred tons of what? Well, they can't not. Well, there's a difference between picking them up, maybe picking them up a little bit, and putting a rug under it, and then pushing them up the ramp. That's the difference. Because it's less force to do it that way than it is to pick it up. Okay? You're still exerting a lot of force, and I'm sure it was still really, really hard to do, but it was doable. It was able to be done that way. Okay? What's with all the dancing?
Look, it's just a happy day.
Well, I'm glad that it's a happy day. But, all right, and the mechanical advantage here is the length of the incline versus the height of the incline, right? So we talked about the triangle and the ratio between the length of this ramp and the height of the ramp is the mechanical advantage. So the longer the ramp for the same height, the bigger the mechanical advantage. All right? And we talked about how a wedge is kind of like an inclined plane. Now, how is pressure connected to the wedge? Right, it's going to go in and push out, right? But if you have a needle and you're going to give somebody a shot, like this, right, you have a certain amount of pressure that's going to be required to get into his skin. I don't know, maybe. Give a shot of energy, shot of confidence that you can take written questions. Right? Now, if you look at this then, we talked about, I mentioned why with the wedge, it's better to have a sharp one or a needle knife. It's better to have a sharp blade than a dull blade because that's going to reduce the area. If you reduce the area, what happens to pressure?
It goes way up.
Goes up, right? Okay. If you have somebody who is walking on your back, you'd much rather have them in bare feet than in high heels. Right? Because in high heels, you're going to decrease that area, therefore you're going to greatly increase the pressure. Right? The bigger the surface when it's pushing down on it, then the less pressure that you actually feel. So you can handle bigger forces if the pressure is spread out. Right? Over a bigger area. So if I was giving, I guess the CJ's going to have to give the shot to Bella. If I give a shot to Ella, then if this is dull, if the area is bigger, so what do I have to do? You have to increase what? Well, the pressure is going to be the same. You have to increase force, right? So instead of going like this, I have to go like this. Well, you can, but either way, it's not going to be as pleasant for her because it's not only are you have to put more force on it, which is going to make it bruise more, but also if it's a bigger area, it's going to spread out the flesh more. Okay, so that's why we like sharp needles if you have to get shot. Right? We don't want dull needles. You don't want dull knives if you're using a knife. Because then you have to increase the amount of force that's involved. You increase the odds that you cut yourself. Because it's going to be more likely to slip. It won't stick on the surface as well. So, a sharp knife is less dangerous than a dull knife. Yes? Yes, but you're much less likely to get cut by the sharp knife. Because you're not pushing as hard and it'll stick into the surface easier. All right? So, if you have dull blades in the kitchen, don't worry, don't use them. I had my wife's cousin, not last Thanksgiving, but the one before that. I told her the same thing because she kept complaining about how dull this blade was and she was peeling potatoes. No, that's crazy. Surface is paper ended up in urgent care. So then, of course, a little bit later on, I sent her all the literature on why Fairblade is safer than Zollway, but I'm not sure you can appreciate that, but whatever. So, the point is, what? Well, you know, sometimes people have to learn the hard way. Well, they should learn the easy way, right? Remember the highest form of wisdom is when we learn from others' mistakes. But you shouldn't have to learn from your own mistakes. I like how you brought it around there, but okay. So then the screw was basically another form of the inclined plane, right? Where you're just increasing the distance that it's going into the surface, right? But what's really important for today is this idea of the lever. All right, and crucial to understanding the lever is knowing that where the fulcrum is. All right, settle down, everybody. All right, the fulcrum is the pivot point. All right, so wherever the pivot point of the lever is where we say the fulcrum, and that determines which class of lever it is. And the class of lever will tell us, kind of what it's good for. Yes. You should know the levers, yes. Yes. Well, you don't have to memorize the other type of machines, but you need to know how to find mechanical advantage. So, you have the first class lever. Basically, the first class lever is anytime that we pry something, pull it out of anything. Yes. I haven't decided yet. I might. Mr. Costello, I think this is the most questions you've ever asked in the class. You must be really concerned about this exam. Yeah. All right, well. Probably, but, it's all about the learning. Now. All right, so. Anything that we pull with is going to be this first class lever. The fulcrum is between the input and the output force. All right, and basically you're pushing it one way, and the object is moving the opposite way if it moves. Right? And how do we make a first class lever better? Well, we want to get. Remember that the ideal mechanical advantage is based on the distance, and we'll just write this over here. We'll say input to output distance. Okay, so in all cases, if we want to increase the mechanical advantage, we've got to increase the input and decrease the output distance. So, if we want to have a good first-class lever, we want the fulcrum as close to the output as we can, and we want a nice long arm. We want a nice long arm for the input, right? So, and if you're prying something, like if this is your prying tool, you don't want to move your hand down close to where you're prying it, because you're losing mechanical advantage that way. You want to keep it as far back as you can. Because that's where the force goes, the distance to that where it's being pried is going to be a major factor in terms of how much of an advantage it is. So if you have a screw or a nail that's not coming out very well, you can get a longer crowbar. Right? That's going to give you more advantage. Keep that in mind, that distance as well as the distance, and usually you can't control the output force too much. In situations like this is pretty much that. But you can increase the arm on the input. All right? what one of the annoyances is if you ever have to change your own tire is the wrench that they give you with the jack is like this long, and you're trying to take these lug nuts off that are on with impact guns from these shops that it's nearly impossible to do. It's not easy to do. So, okay. The second class lever looks like this. You're going to have the fulcrum still. You have the fulcrum at the end of it. And the output and the input are going the same way, but the input is outside of the output. Right? So, the wheelbarrow is a good example of this because you have the output force, which is what's being picked up here. Notice that when wheelbarrows are designed, they don't move this up here. They don't move it away from the wheel. They move it as close to the wheel as you can get it, because that's going to allow you to pick things up easier than if this were up higher, and as well as having long handles. Right? But the fulcrum then obviously is at the wheel. That's a second class lever. The same thing applies with the mechanical advantage. You have input over output. So you got to decrease that and keep that output as close to the wheel. Increase the arm length if you want to make that better. Okay? You do lose some control that way, though. Okay, now the third class lever probably is the one that has the least mechanical advantage, but usually what this is used for is to change the direction of something, right? To move it in a different sort of direction. So you have a rake and you have the fulcrum up at the top of the rake, right? But if you want the input, if you want to increase the strength there, you can kind of move your hands down this pole in order to brake harder, like if you have something you're tearing up. But that's the third class lever. All right, no big deal. All right? And I have some examples and answers down there at the bottom. Make sure you look through those. We have two other tools that we want to look at. Okay? Wheel and axle. This is like on a car, how the tires on your car are put on. The wheels and the tires that are in the back. With an axle and the wheels at the end. Now, notice the mechanical advantage there. And how this is found. You have to look at the radius. Listen, look at the radius of the wheels. Right? And if you have a bigger wheel, then you're going to get more mechanical advantage. And you want a smaller axle. Right? So you decrease the axle size, you increase the wheel size to help it out. Now, there's going to be some limit there, for cars and whatnot, because it has to be load bearing. Can't make that too thin, otherwise it's going to break. What? Well, and you notice when they have the four-wheel drive that they use bigger tires. The back. So that's just giving it a bit more power. In order to, because you have a more mechanical advantage, therefore the work can be done quicker. Okay? Simple enough. And have a what?
You can't do that because I can't go to inside.
That's true. It would be hard to do social distancing with a group project. I think I'll pass, but it's an interesting suggestion. Okay. So, finally, you have the pulley systems, right? Things used just to pick things up so that the loads can be moved to a higher elevation. And Basically, this is just based on the number of ropes that are there. Right? And number of ropes is just another way of saying how many gears are present in the pulley system. And the more that are there, you're going to increase the distance of that rope. Remember what that does for work or for force. The more you increase the distance of the pull of it, the more the force goes down. So basically, each rope here, each going around the wheel, is going to increase the distance and therefore decrease the force that's involved. So if you have a really complicated pulley like this, then you're going to have to use a lot less force to pick up an object. Right? Because the distance that it has to go through is going to be a lot greater. Now, this is going to be really slow because it does have to go through all that distance with the rope, and that force has to be transmitted through that. However, if it's a really, really, really heavy object, it's certainly worthwhile to do it that way. Right? So basically all you do when you look at this is you're going to look at this and either count the number of ropes or the number of wheels. So like this one right here with this guy, 1, 2, 3, 4 wheels or 1, 2, 3, 4 ropes. So we would say this has a mechanical advantage of 4. What does that mean? Well, that means that if you're picking up something that weighs 1,000 newtons, it's only going to feel like 250 newtons. So that's 1/4 of the weight. Right? And the more wheels that go here, like this one I think has 6, so then that would be the weight divided by 6. Right? Obviously, especially if you have to do a lot of them, that's going to be a nice thing to have. Right? Just if it's humans that are doing it. Or machines, right? That's easier on engines if these engines have to move these objects. Okay? So, those are our simple machines. Again, what your job is to go through this last homework assignment here and do these answers. There's even some more descriptors in the beginning of the homework assignment. Just do what's called 9. And make sure you can do those mechanical advantage problems. Once you get through a few of them, I don't think that you'll find them very difficult. They're really not that hard to do. It's just looking at the ratio between them. All right? That's it. So if you have questions about that, let me know. Again, stay where you are. Keep your mask over your faces or out the nose. Don't get lazy with that. And then, I can't remember, was it 22? I think it's 122 is disinfectant time. So, somebody from your table could do it. Okay. And that's it.